But before getting into the details, let's look at the schedule first. So I'm going to go through the calculation and then the slides for sensor actuators. It's critical since there are some examples of the Arduino code over there for the homework assignments over here. You couldn't see anything because I didn't click this button. All right. So yeah, slides with examples of the Arduino codes. And then joysticks. It's a joystick. I don't know why I put a joysticks over there. Is that because I use chopsticks every day? Joystick, okay. It's a full tutorial, follow it, because we're going to use it for the car. And homework 5 will be the whole tutorial. Just follow it and report whatever you did by following this tutorial. And another thing is since from the email I sent to you already, the 3D printing, I appreciate your help with that one. And I'm going to give you credit. So if you just make it work and everyone can get 100 on that one. So I expect that one will be done by Friday this week. And I expect a very simple report. You just need a homework 4 on your website by just showing some of the pictures you printed, the parts you printed. So there are 2 groups. One group directly use the black ones, the other group assembly and print a simple thing from that. And after we went through all the joysticks lectures, and there won't be any lectures next Monday, Wednesday, because you guys are going to work in 602. I will provide all the parts for you guys to make it work. And there will be a homework 6. It's a little bit long, so expect to spend a lot of time on that. And so these are just some real world problems. You need a demonstration, videos, and anything will support the work you have done, and put everything on the web page. And do not directly post, if you look at the notes on the top, do not directly post your original code on the web page, but just let me know the name of the file and place all the files in one of the folders on your on the server. So that one will take some time to finish. And I didn't give you time to do it during the class, so you have to, either these 2 time slots or here if you got some time over there to finish that. So you have access to 602, so you can, stay in the lab and do this every time, anytime you get a chance. And there's a very simple tutorial regarding RFID. It's very simple and very interesting. So it's an everyday technology. I really want you guys to understand what's going on, how that works, right? I mean, how can I get a data being sent back from a plastic, how that works. And then a strain gauge, I'm 50% done with the tutorial, but I will get that posted pretty soon. And then we'll move into our 2-wheel balancing car, which takes a month to finish from beginning. Okay, that's a plan for these recent weeks. Now let's look at the strain gauge. Last time we were at the quarter gauge. So why the strain gauge is significant? I mean, why do we want to talk about strain gauges? Sounds like nothing. There's nothing about robotics, right? Why strain gauge? What's that one used for? So if you talk about the sensor, the strain gauge is a what type of sensor? It's sensing what? No. String gauge, string gauge. Voltage. So sensing voltage. What is the sensors to sense voltage? Come on, you guys. So after this class, you guys should be very familiar with this type of questions, right? So all these are real world applications, right? You should be able to answer that question in a second, but you just didn't. It's pretty frustrating. So what's a sensor to sense the voltage? Come on, ADCs. Analog to digital converters, right? You got your Arduino, you got an A0 to A4, you got all these analog inputs and being converted into, they'll be converted into digital signals directly. Okay? Is that clear? We want to convert everything into voltage. And now you directly have voltage, just ADCs, right? Because you want ADCs in the middle of the analog environment and your microcontrollers. You need ADCs to do it because the sensors will convert everything to analog voltage. And you get an ADC to sense the voltage and send it to microcontrollers. So the sensors to sense voltages will be ADCs, analog to digital converters. Do you have an ADC on your Arduino board? Yes. How many bits? 10. Okay. Can you buy a ADC integrated circuits? Yes, you can buy it. $2 sometimes. Okay. String gauges. So last time we did the quarter gauge, and now let's look at the half bridge. Sorry, not quarter gauge, quarter bridge. And now half bridge. I've been keep saying that, you know, you want to be very clear about what you want to do so you can prepare for that. I didn't have a plan at the college because I know I'm going to pursue a PhD degree. And the reason is I like summer vacations. I got 3.5 months in summer and one month in winter. So that's why I know I'm going to pursue that. But you guys probably want to get a job, right? Not many of you guys are going to pursue a graduate degree, probably. You know, I highly recommend it, but I know a lot of you guys are not doing that, which is fine. But you want to prepare yourself for a job. So the reason that we can have 2 string gauges, so just let you know, this is a string gauge. So these 2 guys are string gauges, they are not regular resistors. You can see a little delta R is changing the resistance. Whenever you bend it, it's usually, it's called a load cell. So this guy is a load cell. So you guys are going to work with the load cell in that string gauge session. There will be a tutorial created by that. So actually you will be able to design a scale by yourself by using these load cells with a little LCD display and string gauges. But it's not being used for a scale all the time, right? So the reason whenever we are dealing with the sensor, we want to know the sensor is doing what kind of job. So if you step onto the scale, you can look at your weight, right? Sometimes you want to hold the wall to make it look better. I'm not that heavy. And so it's sensing what? You step onto it, and it's sending us, what's the signal is being sent to the ADC. So it's a resistance change. And because you part it up by these 2 points, so the resistance change will be changed to a delta V. So convert the resistance into voltage. And now ADC. All right? That's how I got the voltage. And the voltage carries the information of the weight from the resistance. So it's actually converting the weight into a resistance and then voltage, right? So the weight is being sensed by what? By pressure. So now here it goes. So strain gauge is a what sensor? Pressure sensor. Yeah, you press it, you get a signal change. The pressure sensor. So for pressure sensor, it has very broad application. The scale definitely, but you know, I worked with a company last year. I have talked about that during the microcontroller class. So we designed that ESP32 little board. That one was embedded into the horseshoes, and that's just the one signal collected. It's just for balancing, just sensing the balance of the horse. But also the company also requested another dimension of the signal, which is the pressure. So we're going to see the strikes from the hoof, from the legs of the horse, see if they are balanced on 2 sides. So we can tell if the horse is paralyzed, probably, or lame, I don't know, just imbalanced on 2 sides of the horse. So pressure sensor will be merged into that system. So do a data fusion. So that's another application for that. And also you can think about it, there might be a robot step onto something and you want to feedback a signal to the robot to, you know, see what is that material, things like that. So you may need a pressure sensor as well. So that's the sensor can sense pressure. How do we calculate this one? Delta V is V2 minus V1. And so it's a voltage divider. So V excitation. So Vx means excitation voltage times. So we're getting V2 right now. So this is V2 is Vx times R plus delta R. That's the voltage here over 2R. Because this addition of these 2 terms will be 2R. So that's a voltage divider. It's going to be V2 minus V1. So V1 is this guy is a half of Vx because it's just in the middle. Got 2 R's to split that Vx into 2 halves. So V1 is 1 half. And then Vx times 2R, R plus delta R minus R. Is that correct? Cancelled. So it's Vex times delta R over 2R. So from last time, we did a quarter bridge. In the quarter bridge, you just look at the notes. I don't want to run through it again. But for the quarter bridge, delta V equals to Vex times delta R over 4R from last time's notes. And now, if you compare these two, a quarter bridge compared to a half bridge, which one is more sensitive? Half bridge, why? Yeah, yeah, because if you have a same delta R, it's going to output a higher voltage. It's more sensitive. So I give you an example here right now. I actually purchased a lot of strain gauges, this little tiny resistor films, and I connected. I just grabbed 3 resistors from the drawer in the lab, and I plug in one strain gauge directly, not with a low cell. It's not being attached to anything, just a resistor film in here. And then I'm trying to measure the voltage, the delta V over here. So definitely this one needs to be amplified and then being sent to the microcontroller. And I was trying to bend it, with my finger, and to bend it a little bit with my finger, and then look at the changes in Arduino's serial monitor. But I couldn't see the change. It's either going to the maximum, the highest value, or the lowest value. Why is that? So a little tiny film, which is a strain gauge, the resistor traces on the film. And I was trying to use my finger to bend it a little bit, upwards or downwards, right? So I can see a change of the R. And I was hoping that it's being amplified and being sent to the Arduino. I can read a number in Arduino serial monitor. It's not giving me any intermediate values. It's either the maximum or the lowest, the negative maximum or the positive maximum. What was that? Yes, yeah. So the changes will be tiny on the low cell. If it's being attached to the metal, for example, here's a low cell, you attach that film here or here, you bend the metal, so it's not being deformed that much. So you can see all these variations in the middle. If you bend it, just bend the film by your finger, first, it's going to saturate the output. Second, you'll damage it. That's what I did. Oh my goodness. Never mind, I bought 20, so. And then full bridge. So is that making sense for this one? It's a low cell, it's a metal piece being mounted somewhere, and then you give a pressure here or push it upwards. And you are getting a different R. For example, this is this R, and this is this R. If you attach the top film in one direction and you flip the other one and attach to here, so whenever you bend the top one, it's increasing the voltage. You are getting a positive delta R, and the bottom one is giving you a negative delta R. Something like that. And you connect these two to the bridge. But the question is, how can I make sure these two delta R's are the same? We'll revisit that later. So I need to take a look at the details, what is inside the low cell. I'm going to give you a picture on that on a tutorial for the strain gauge one. Okay, that's a question to think about. For the full bridge, R plus delta R, R minus delta R, R minus delta R, R plus delta R. So what about this one? Delta V equals to VEX. Still V2 minus V1, right? And which is VX it's going to be the voltage here, which is R plus delta R over 2R minus R minus delta R over 2R, and which is VEX So this guy is even more sensitive compared to the half bridge. Okay, so that will help you guys to finish the first problem in homework 6. And now let's come back to the slides, see where we were last time. Yeah, I think we were talking about the strain gauge. That's why I moved to the paper calculation from Wednesday last week. And this is a load cell I bought. So you do need that load cell, and that's a strain gauge being mounted to the metal piece on the top. So these are different types of load cells. So one of the most important application for that one is the scale, right? Either the bathroom scale or Z scale for to be used in the grocery store. Wait, where's the, okay, so that's a quarter bridge, half bridge, that's application for how you can mount the strain gauges on the load cell, and that's a full bridge. And we just did the calculation on that. And you need an amplifier. Why do you need an amplifier? Because the resistance change is very small, and you need to amplify it. So the amplifier amplifies a voltage. Because according to our calculation, we got a delta V, right? That's what we got. And when I amplify that delta V, that's an IC chip you can buy. So that's a load cell. Here's the IC chip. It's HX711. Everything has been soldered on the PCB board you can buy. It's a pretty mature product. Flip it on the back. It's made in China. You know, it's all these like $5 you can buy 10. You know, how can I compete with that? Anyway, but these are 24-bit delta sigma ADCs. It's very, very sensitive, 24-bit. There's also a library available online. You can directly buy it. You can directly download it and use it for your application. So if you look at these communication ports, can you tell what is that? Let's come back here. What is it? Output protocol. So if you see SCK, what's the protocol? What is that protocol? Isn't it SPI All right, so it's SPI. SCK is a label for SPI's clock. CK clock, SCK is for SPI. And for I2C, remember what's the name of the clock? It's fine, we cover in microcontroller, so I just want to ask them. So what is I2C's clock? ICL, yeah. Made it. All right. That's SPI, right? That's SPI interface. Okay. Using all these libraries are very convenient. You don't need to dig into the details of it to write a driver by ourselves. We will write a driver by ourselves in the spring, just to practice, right? But we won't write it every time. Otherwise, just write the drivers will take you probably 3 weeks. Let's don't do that. And now the next chapter is regarding the temperature sensors. And we do have so many different types of temperature sensors. They are the most common sensors available on the market. But it's easy to use, but not that easy to be an engineer that you can tell which one to use since you have so many options. So thermocouple, you have used that in measurement and instrumentation, that class, I think. And it's just like 2 different types of metal materials, and the temperature change here at the joint of the 2 metal pieces, it's going to give you a voltage difference. And definitely that voltage difference is not big enough for ADC to sense it. So you need an amplifier. So this board has amplifier on it. So it's a module to be directly interfaced with your thermocouple. And there's another IC chip you can buy from Maximum. If you see Max something blah 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 blah, that's Maximum. Maxim. So MAXIM. It's a integrated circuit company. I think in Oregon, headquartered in Oregon. There's also a Silicon Valley branch over there as well. It used to be a pretty big company in the past like 40, 30 years. But now it's just not as big as before. When they are cut the employees, cut the departments, usually there are like 2,000 people are going to lose their job in these type of companies because of competition. So here's a thermocouple. You got a voltage difference is a delta V. The delta V will be sensed by I'm pretty sure there's a differential amplifier inside. Okay. So what's the next one? It's microcontroller, right? So SPI as well. So what is that one? If you see AD blah blah blah, what's the company? Analog device. That's probably the top 3 companies making analog devices. So the name of the company is just directly Analog Device, and which acquired linear technology, who invented all these LT blah blah chips and also LT spice. So AD acquired linear technology, not long time ago, actually a few years ago. So AD is one of the biggest player on the market. So you can see that this is a instrumentation amplifier. We have 3 op-amps. Okay, I used to give a quiz to you guys to calculate the gain of the this instrumentation amplifier, but I'm not going to do it here this time because you guys were not in my analog. the performance of this instrumentation amplifier is just way, way better than a single op-amp. Keep that in mind. If you are trying to amplify anything, analog signal, that's the first choice. Just directly grab one and amplify it. Do not try to make a inverting configuration or non-inverting configuration trying to amplify it. So the instrumentation amplifier is the first choice. Just grab one and do it. And you don't need any feedback for that configuration because everything has been fed back inside internally. See all these negative feedbacks? Do you see that? Can you see my mouse here? Probably not. Okay. Sometimes you're looking at an op-amp and they directly do a triangle over there, like as a single op-amp. And you are saying, there's no feedback. How can you make signal be amplified? So see here, there's no feedback. So that's the amplifier, overall amplifier. The output is not being fed back to the input. Because everything has been fed back internally, right? This is not an op-amp, this is three op-amps. If you look at the schematics for some of the designs, don't get confused. If you see a triangle shape, there's no feedback, you get scared. Like this design, ridiculous, right? That's just not. It's just a triangle to represent the instrumentation amplifier, which has a higher performance. So the story for this one is we were not using analog, but circuit one I think covered that, right? So whenever you are trying to use a op-amp like this, you always need a negative feedback. So I have been telling that story in analog or circuit one all the time. That's why we talk about the negative feedback over there. And if they are already designed inside, and I don't want to give you assignment to derive the voltage gain for this one. It's not really robotics. So you just need to know how to use it. Very simple, straightforward. You grab this IC chip from the drawer and plug into the board. And you got a differential inputs to connect to delta V. You got delta V or some couple delta V, differential V. It's actually this one is this, but this one's being shortly around. They are talking about, hey, this is a 1 megaohm. What is that one? What is that 1 megaohm doing here? So whenever we have a cap, we design voltage regulators, right, in the past. And we usually have a cap to stabilize the output. If we are trying to supply DC voltage to the external circuits, we usually hook a cap to that pin. The cap is like working as a reservoir and also performing like a low pass filter. High frequency will pass the cap and be short to ground. So all the high frequency components is charging and discharging that huge bucket. It's going to be smoothed out because it's not able to charge and fully charge and discharge that cap. That's why whenever you need a DC voltage, you need a cap. Or if you want to get rid of all these AC high frequency noises, you need a cap. But now it's not a cap. It's a huge resistor. So what's the function of that huge resistor? So keep one thing in mind, I just remind you guys, right? As an engineer, you want to keep that in mind. I'm going to repeat this all the time this semester. So we use a cap to remove what? High frequency stuff, noises, ripples. Because there are so many caps in the circuits, it just confuses you, right? Like there are so many caps everywhere. See here. You see some of the low-pass filters. So since I'm going, yeah, coming in there. Low-pass filter. So to stabilize what? So that stabilize. So caps are used to remove high-frequency components. So which stabilize DC voltage. Okay, keep in mind. Do we have a DC voltage here to stabilize? Do we have a DC voltage here to stabilize? Here. On the top. Yes, we do. Now what is that? Vx. Remember we just did the derivation, right? We just did it. We got a Vx at the top. That's the power supply on the top. So it can give you a delta V here. And the delta V is being amplified. It's delta V, input, analog input, in A, analog input, differential voltage. It's being amplified. The delta V is being amplified. PGA, programmable gain amplifier, different options for gain, and ADC. So amplify it first, so the voltage delta V from the string gauge, amplify it first, and digitize it, and then interface, send it out to the microcontroller using a digital protocol, SPI. There. What's this guy doing? So any of the AC noises will be directly short of ground. So nothing, smooth, ground. Can I find another low pass filter somewhere? No, that's it. Got two. One here, one there. Same for this one. I mean, that's an IC chip. I got a VCC, I got a ground. You just need a DC power supply. It's powered up, right? Why do you need a cap in between? So it's going to keep this DC voltage a pure DC without ripples. This guy will short all the AC signal to the ground. It's hard to imagine like how the AC signal can pass a cap. Right? It is hard to imagine. I have to admit that. I couldn't even see the way they thought out. Just remember, caps are used to remove AC noises or high frequency noises. So AC voltage can always pass a cap. Keep in mind, you got a capacitor, you got AC signal here, it's gonna pass. It's open up the multi-slice and simulate it, you'll see that. Why is passing that cap? The cap has two metal plates and dielectric material in the middle is like a disconnect circuit. Why is passing that AC? Because it's checking polarity. Checking polarity, and it's going to generate an electric field in between the two plates. So whenever the AC signal is charging and discharging this plate, the electric field will charge and discharge the other plate. So charges get into the plate and also get out of the plate all the time. That's why it seems like this passes the cap, but actually it's not. It's an electric field attract. So it's going to charge out the plate on the other side or discharge it. So the charges are moving back and forth. That's why it seems like it's passing, but actually it's not. If you have a static voltage, we got static voltage here, definitely it's not going to reach here to DC, right? So at the moment you turn the switch, there might be a spike up here, but after a long period of time, there's nothing here. It's just a ground. So the DC cannot pass the cap. The AC can pass it. Just remember that.
But when the AC generates the DC, the other side is when AC it's passing the cap, it's moving DC current on the other side, right?
No AC. No, it's always AC. So AC can pass the cap.
Right, but once it passes, does it behave like AC also, or just
Like AC also. If you probe it, it's the same voltage, same sine wave.
okay?
It's just open on these slides and try it. You'll see this. Very interesting.
So well, this one, let's just come back to this one. After this, we'll call it today.
Here. I'm just repeating, okay? AC is used to remove what? No, so a cap is used to remove the AC component. So this one is doing what? So a huge resistor is to block AC, but conduct DC. Why? So a resistor, huge resistor, seems like there's it's a disconnect circuit because the resistance is so high. It's like iron, such a high resistance. But the thing is, it's not iron. It's not disconnected. It's still connected. So a huge resistor can still conduct potential. Keep in mind, but keep the current flow in the resistor very, very small. Very, why the current very small? Ohm's law, right? Same voltage, huge resistance, no current. No current, no voltage drop. So it's a perfect potential conductor. So what's the potential here? 0. What's the potential here? 0. Perfect ground. The thing is that by adding this one, it's going to block any of the AC signal, which because all the grounds are have a common ground. If there's anything being, it's like some of the kickback currents or something being sent, high frequency stuff, won't get into this one. That's a really sensitive thermocouple sensor has a very tiny DC voltage up here. So by doing that, you can ground this pin, but not introducing any of the AC noises to this pin. It's a huge resistor. Remember that? A huge resistor blocks ACs. The reason it blocks ACs is because it has a tiny bit of current because the resistance is so huge. So when the AC is trying to charge and discharge anything, it's not able to do that. The current is so low. Okay? So huge resistor blocks AC but conducts potential, which is DC. Or capacitor transfer AC but block DC. That's a conclusion. I think this helps you to understand these schematics from the data sheets or from the online resources you can get. We'll continue working on this on Wednesday.